obligatory slide, vendor neutral. This is not about anything I build or any products I'm involved with. It's about just trying to help you understand how this kind of science can be used to improve your efficiency in your data center. I'm here for you. This is an educational piece. I like to make these interactive. If you have any questions, ask them. Don't wait till the end. Just ask them. This is a discussion. I think I can get through most of this material in 45 minutes. And if not, it's probably better if you've got a question, somebody else has it too. There are no dumb questions. There's no bad questions. It's all just sharing knowledge with each other. So what we're going to talk about today is how to predict energy savings by optimizing airflow. Most all of you have air-cooled computers. Liquid's great. Liquid's a little more expensive. They'll always be air-cooled because of the economics. Liquid's just going to be more expensive. That's just the bottom line. So you're always going to be dealing with airflow. Even in liquid systems, there's airflow. So, at some point, particularly with rear door heat exchangers, there's airflow. So we're going to be talking about airflow today. We're going to be talking about it as it relates to PUE. And I'm going to also be discussing with you a new specification called TC 90.4. 90.4 is a spec for energy efficiency as well, and it relates to PUE. We're going to talk a little bit about it. A little bit of background on myself before we get too far. Paul Bemis. I have a background in mechanical engineering and electrical engineering. Undergrad mechanical, graduate work electrical. I was in the computer business for many years. I worked for Hewlett-Packard, electronics packaging first. Later on, parallel processing, high-performance computing. Ended up on the business side and ended up working in simulation software later in my career, which is where I am now. So let's talk about first PUE. Most everybody here knows what it is. I'm just doing a level set here because I don't know where you all are with respect to understanding these things. PUE is a fairly good metric. It suffers from a few things. It is in the numerator total facility divided by IT energy. Total facility includes, of course, the IT equipment itself plus all the stuff extra to make that data center work. Okay, so that's the ratio. Now, the point here that I always try to make is that numerator, if you take IT energy out, the numerator is dominated by cooling power. And this pie chart shows this. It's been around a long time from uptime. And it's showing you that it's really the cooling unit itself that's driving most of this. I know there's a pointer here somewhere. Most of this cost. It did work. It worked a while ago. But anyway, it's chiller power, fan power that dominates it. UPS leakage is getting much better. The UPSs are getting more improved. The PDUs are getting more improved. So you're still dominated by cooling in that numerator. So it's really cooling power is the dominant parameter. And whenever you're trying to optimize something, look for the dominant parameters. What are they? Cooling power. It's the elephant in the room. It's shaft power. It's the thing that is causing the heat to get out. And what you're trying to do is optimize that. You've got IT energy over IT energy there as well. Now, what you run into here is that for many data centers, the cooling power, particularly new data centers, where the IT energy is low early on, that number is going to look horrible. PUE is going to look horrible. How to improve the energy efficiency? We talked about this a little earlier. Drive up the IT load, and then your PUE will go up. So it's not really a measure of energy efficiency, PUE, and it suffers a little bit from that. So in fact, let me just back up and say that in this relationship here, if we were to take the IT energy out of the numerator, it would be essentially the inverse of the new TC 90.4 spec. TC 90.4 is looking at cooling energy versus IT load. What does that ratio look like? Now, the IT load in the new spec includes other things like PDU inefficiency and leakage. It's the whole thing in the denominator. But in the numerator, it is cooling power. All of it, by the way. That includes the fans that are driving the air handlers that are in the room. It's the fans driving the air handlers out on the top of the building. It's the chiller. It's cooling tower pumps. They've got it all in there. So it's an interesting spec that's getting quite a bit of attention, I think, these days. But let's take this thing apart a little bit. Total cooling power equals fan power. These are the fans that are in the room. These are the fans typically, if it's a chilled water system, that are on the fan coils. They're often called CRAHs or crays. They're air handlers, computer room air handler. They're often also called cracks, although that's, computer room air conditioner, although that generally is referred to with a DX system, so it's got the compressor in it. That's generally what people refer to. So it's the air handler in the room, plus whatever's in that room, the cooling load, which is all the IT load and any leakage from the PDUs and everything else, divided by the efficiency of the heat pump, coefficient of performance. How efficient is the heat rejection system? So data center is fairly simple. It's heat in the room, and you're going to try to dump it. You're going to try to dump it back out. Now, what you'd like to do is do that at a ratio that's pretty good, right? A ratio that's pretty good is around 4. That means for every kilowatt of power that I put into the data center, it takes me about 0.25 kilowatts to pump it back out. That's a good day. That's pretty good. I've seen them much, much worse than that. I've seen them at 1 to 1. For every kilowatt you put in the room, it takes another kilowatt to get it out. And airflow generally is the reason why. So the total cooling load includes the racks themselves. They're the power going into the rack, and also the power driving its fan, plus the PDU leakage and PDU power dissipation. Not the kVA going through the PDU. It's the residual heat that the PDU creates because it's not a 100% efficient device. So it's leakage. And UPS leakage and heat and fan power of that air handler. A lot of people forget that if I put a fan in a room and put wattage into it to spin the blades, I have to then dump the heat back out of the room. It's a heater. Although it's moving air, at the end of the day, it generates heat. I've got to dump that back out too. So things like putting more fans in the data center aren't my favorite thing because at the end of the day, they are heat-generating devices. And although they have a good purpose in many cases, in other cases, they're just generating heat. So total cooling power is the fan power for the air handlers. That's going into the room. Plus here on the numerator, you've got rack power plus PDU power plus UPS power. Those are leakages. Fan power again. So you pay for it twice. You pay for it once to put it in the room, and you pay to pump it back out. And that's how it works. Now in the TC 90.4 spec, they add a few other things in here as well. They're adding in, of course, any cooling tower fans. They're including pumps. So all things related to cooling go into that calculation. So cooling system efficiency is really shaft power. It's the power required to pump the heat back out. And it's usually done through shaft power. It's done through a mechanical pump. It's done through a compressor. That's generally how it's done. Whether it's a DX unit or it's a chiller, it's mechanical. It spins a shaft power, that drives a compressor. The coefficient of performance is how efficient that chiller is. Now, you'll see chiller efficiencies in documentation listed kind of funny. They go kilowatts per ton. I love this thing, kilowatts per ton. Oh, can't you give me the same units? Right, because you convert a ton to a kilowatt. It's a ratio about 3.541, something terrible, right, that you can convert it. And then it's kilowatts per kilowatts, and that is the coefficient of performance. And generally, as I said, on a good day, they run about 4. If they've got economizers, of course, they can be much higher than that. And they are not a constant. It does vary based on outdoor air temperature. It varies based on wet bulb temperature and things like that. So it varies as a function of time. It is not a constant, although you can develop an average for a year if you measure it. And generally we have to make some assumptions somewhere, so we work with an average COP. So for most data centers, I find they run in the range of 2 to 3. If you look at that TC 90.4 spec, and they have something they call the MLC, mechanical load component or calculation. It's really the inverse of the COP is what it is, and it's a system level COP. In other words, if you look at just the chiller number alone, it's a best case situation. kilowatts per ton. You look at the chiller spec, you say, well, it's got a ratio of about 3. The COP is 3 or 4. Well, that's under a laboratory test. That's under the best of conditions. And it's not a system level number. In other words, it doesn't include the water tower pump. It doesn't include the pumps pumping. It doesn't include the fans. So what we're trying to get at really here is the overall system efficiency, the overall cooling system efficiency for your specific data center. That's really what we're after, and that's what they're chasing with TC 90.4. So it's a good specification. I think you're going to see more from it. But at the end of the day, COP is just the amount of work required to dump heat. It's just a ratio. And it's true for all, I found it. It's true for all devices. It's true for your refrigerator. It's true for your air conditioner. It's true for your data center. Coefficient of performance is something you should get a feel for. You should try to understand what yours is at your data center. It's fairly easy to figure out because you can go to your UPS and see how much load you have going into the room, at least the IT load going into the room. And then hopefully you can also go to your transfer switch and find out how much power is going to the cooling system. It's the ratio of those two numbers, if nothing else, even if you do it at a spot, even if it's a spot check on a given day, pick a hot day and then pick a cold day and see how they vary. Compare the two numbers. It's the ratio of those two numbers that really makes the difference in energy efficiency of your data center. And it's important to know where you stand. Now, of course, chillers are shared. You don't always have your own dedicated chiller for your data center, so you have to prorate it a little bit. Prorate it proportional to the IT load, that's all. In your room, if you've got 30% of the total chiller load in your room, take 30% of the energy that the chiller's using. So it's important to kind of understand where you are with respect to efficiency in your own data center. And the guidelines that TC 90.4 put in place give you, as I showed here, a ratio of 1.8 to 2.6. It's not too bad. Pretty close to the average that I have been suggesting that I see in data centers normally. Okay? Now, the other thing is the reason that it's important that we talk about airflow is because it influences chiller efficiency. The chiller is most influenced by return air temperature because it's trying to dump heat to the outside atmosphere. And therefore, its temperature to dump needs to be higher than the outside atmosphere. And the bigger the difference, the better off it does. Heat exchangers work that way. They're more efficient when the delta T gets higher. You think of it just like voltage. It's voltage across a resistor. It's the same thing. It's potential. It's the delta T across the heat exchanger that makes it an efficient device. And by the way, it's nonlinear. It gets really efficient as the delta T goes up. I'm showing you a linear relationship here out of the ASHRAE catalog and one of the books. And you see it's also fairly linear within a certain range. It's not completely linear. I've been chased around on this before. But we have to make some assumptions. And for all practical purposes, you can assume it's fairly linear. You're going to get about 3.5% efficiency improvement in your chiller for about every 1.8 degrees Fahrenheit. Those are tough numbers to kind of remember. But you can think of it as, a percent per degree is not a bad idea. All right? And it's fairly flat in the range that we're talking about. So if you can raise the set points of your data center, supply air temperature in particular, which makes the return air temperature higher, if you can turn up the set points, you're going to get more efficiency. If you raise it about 10 degrees, you're going to get about 20% efficiency improvement in your heat rejection system. It's about where it ends up being. Okay, so it's important to be able to raise your supply air temp. So the first question you think about when you say raise supply air temp, am I going to have hot spots? Now the only way you'll know really that you're going to have hot spots is to model it, is to try it, have a mechanism for trying it out. And I am an advocate of modeling. I'm in the modeling business because it's airflow. And managing that airflow and knowing where that air is going is very important to a couple different things. We talked about the heat exchanger, but also hot spots, getting the air to where it needs to go. You may have enough air coming out of the air handlers, but you got to get it to the right place if you're going to have it improve the efficiency of your center and if you want to try to raise the supply air temperature. So a couple definitions here. Bypass airflow is too much air coming from the air handlers and it goes right around the rack. It doesn't go through it. In a perfect situation, you only want to deliver the amount of air necessary in order to cool your IT equipment. No more, just enough. Okay, and they have a ratio for that they've come up with called RTI, the Room Thermal Index. The amount of air being supplied should be equal to the amount of air that the servers want or need. And no more, because if you have more, it's going to blow by the top, it's going to bypass, it's going to go back to the evaporator, and it's going to reduce the efficiency of that heat exchanger because the return air temps are too low. You want them high. You don't want to cool off the return temp. Question?
How do you arrive to that RTI?
The RTI number, he wanted to know how do you arrive to RTI. I'll show you in a moment, but to answer the question, RTI is a ratio of how much the servers need divided by how much you're giving them. Okay? Well, what you can do as a rule of thumb is assume about 125 CFM per kilowatt. Okay? Even 100 is a fairly good number. About 125, though, is a better number. That assumes a 25-degree delta T. So take the load in the room that you see in your UPS, right? Go look at your UPS. How much load do I have? Multiply it by 125. That's the amount of air you should be giving the room. That's all it needs. Now, you've got to get to the right place. Exactly correct. You've got to distribute it correctly. That's where you come into air management. You have to be able to manage the air. Just because you have enough doesn't mean it's going to get to the right place. So we'll show you how to do that too. The other one that I wanted to point out here is rack recirculation. This is in the case where you don't have enough air. So in the case where you've got a 10 kW rack and you don't have enough perf tiles in front of it or whatever, it's not getting enough air, it's going to inhale its own exhaust. It's going to go right around a circle. Air is very lazy. Question? Yeah, you have to use some kind of air management system. Yes. Now, whether it's containment or whether it's aisle separation or whatever, there are many different techniques for doing that. Okay? So now the other thing to remember is the affinity law, or sometimes called the fan law, or this is a well-known relationship as well. Specifically, the amount of energy required to drive a fan is related to the RPM of the fan cubed. In other words, the relationship is cubic. That's a big jump. So by reducing the amount of air going into the room, I get two benefits. One, my return air temps go up, which is good for the heat exchanger and good for the heat rejection system and improves the efficiency of it. Number two, the amount of energy required to drive the fans in the room drops by a cubic relationship. Well-known, understood fan law relationship here. So if you reduce the fans by 20%, you reduce the energy that's required by 50%. Wow, that's a big hit. That's a big number. And this is where variable speed fans or EC modulated fans have become very popular because you can now begin to move the fan number down. For many years, this was a constant. We were stuck with what we had, and it didn't work very well. Nowadays, the opportunity for EC fans or direct drive fans that can be modulated so that their speeds can go up and down based on a sensor can improve your situation greatly because it'll save you money in fans and also increase your return air temperatures. These two factors, the amount of air entering the room and the temperature of the air entering the room, are the two key parameters associated with saving energy in any data center, whether it's old, new, whether it's, so.
Can we conclude that this is an existing data center replacing a normal fan, analog fan with an EC fan
Yes.
unit?
Yeah.
Power consumption by that particular cooling unit will reduce by 50%?
You can't assume it, no. The question he's asking is, if I move to EC fan and variable speed fan, can I assume energy savings? No, because you haven't yet dealt with the issue of air management. You don't know if turning that fan down is going to cause problems with that server down at the end of the rack row. You don't know that because air has to get to that server, and that's an issue of trying to determine how to get it there, okay? So we'll talk about that a little bit more with respect to air management. But just changing them to variable speed fans isn't the answer. And I've been in data centers where they've converted it all to variable speed fans, and I walk in and they're all running full tilt. They're all screaming. And I feel bad for the people who paid the money to do the conversion to the EC fans because they're not getting their money's worth out of it, because they didn't deal with the issue of airflow management. They just dealt with, and they were sold on this idea of saving energy, but no one ever followed all the way through to do the air management part. Okay? So I mentioned earlier, rule of thumb, 125 per kilowatt. These slides, by the way, are available. You can download them. I already submitted them, so you can go to the site and just pull them. I can also give them to you anytime if you like. It's also being recorded, though I don't know what they're doing with the recording, and it could be the Russians are listening. I don't know for sure.
So it's supposed to be that you'll be able to download the slides with the audio.
With the audio? Okay. In Russian, though, right? Yeah. Just saying, just saying. The other thing I want to point out is there is a point of diminishing return on rack inlet. The ASHRAE spec for recommended rack inlet temp is 80.4 rack inlet temp number, okay? But most of us know that you get to 77F and the fans start ramping up on the IT equipment. So this is kind of a thing we've gotten to know over time. Yes, it's important to increase the supplier temp until the fans on the IT equipment start ramping up, and then now you're it does improve your PUE, yes. Jeff's right. That's because PUE is not a great metric, for energy efficiency in a data center. His point is that the fan in the PUE number, both in the numerator and denominator, are IT, and in the IT number is the fan, which I always wondered about too. What's the fan doing in there? But it is. Okay, so 77 degrees is really where you want to go. Using containment does help. Okay, it is not a panacea. I do another presentation called Containment is not a panacea, because it can bring its own set of problems in, particularly if you mix some rack rows with containment and others without it. I've seen that done a lot. So we're going to do analysis here. I'm going to take you through a couple of examples. And the reason I'm doing this is to sort of show you the mathematics of how to do this and show you the gains that can be made from it. And the other part of it that I think is important is that I'm going to show it to you at both full load and half load. The other thing that TC 90.4 does is it gives a requirement to set the specification of energy efficiency at full load, which everybody designs for. I work with a lot of design build firms, and they're all working at max load. In other words, when I design a data center, I have to make sure it'll handle peak load. Great. Day one, I don't have peak load. Day one, I've got 10%, 20%. How efficient is it at 10% and 20%? No one's ever done the math. Answer is, it's not very efficient at all, right? Because the energy required to drive that chiller is going to be still quite high compared to the IT load. So it's going to be pretty poor. So in the TC 90.4 spec, they have a 50% requirement in there. You have to test it at 50% load in addition to 100% load to see how it behaves itself, which I think is a good idea. So we're going to have a 1 megawatt data center here. It's going to be natural convection with ceiling plenum return. We're going to do a baseline run on it. Always validate your models if you can. This is great to do on existing data centers, is go in and make a few samples to make sure that the model you built actually represents the real world. But in many cases, you haven't built it yet, so it's the best tool you have. And we're going to take a look at putting VFDs in place, and then we're going to increase the supply air temp. That's the sequence that you always go through. First, work on air management, and then drive up supply air temp. It's better than doing it in the reverse, because in the reverse you would have hotspots. So managing the supply air first is always the key, always the first thing to do. So here's my data center. There's a few things. This is a fairly simple design. You've got the air handlers here behind the wall. This is very common to have the air handlers over here. They're in blue. And then the racks sitting here in a hot aisle, cold aisle configuration. The cold is in the center, and it's blowing the the arrows indicate airflow direction through the racks. These at the top are ceiling grills. There are end caps on the rack rows. The reason I point this one out is I've seen these perform pretty well. I've seen these kind of data centers with that kind of design operated at PUE of around 1.3, 1.25. Not too bad. And that's the most cost-effective probably solution you're going to get without going to full containment. And like I said, full containment starts to bring other issues in, pressure issues and airflow issues within the containment itself. This one has no issue. It's really convective hot air. The hot air is coming out the backside of those racks and just, we're using buoyancy in our favor here. It's floating up into the ceiling and being sucked out. Pretty nice design, low-cost design, economical. Here we've got a load of about a megawatt, 160 racks. The rack demand, 139. I don't know if you can all see that, 139,000 CFM. Again, total IT load times 125 per kilowatt. Is it perfect? No. But good engineering is based on calculated assumptions, right? We have to make some assumptions. Otherwise, we can't move forward. And then we test our assumptions and see if they're valid. 125 per kilowatt's pretty good. It's not perfect, but it's pretty good. The supply flow rate in this case, 165. So you see, I already have more air than I really need. I have 139 that I need for the racks. I'm delivering 165. So I know my ratio, my RTI ratio, is going to be below 100. It's not a one-to-one match, right out of the box. Now, here I'm also beginning to look at energy. I want to know how much those fans are delivering. This is a Liebert. We're using CW106s here. And these are 114s that I'm using. 114s, not 106s, sorry. And you can go to the spec. You can get this information online. Find out what your air handlers are running at. In this case, we have 3 motors, and they're generating 3.4 horsepower per motor. Is it kilowatts or horsepower? It's kilowatts. 3.4 kW per motor. And there's 3 motors, so I've got 10.2 kW per air handler. And you can enter that in as your start point, times the number of air handlers, of course. So there's quite a bit of energy going towards cooling itself. Now this is some output from the simulator. I'm going to read this to you because it's pretty small. My RTI here is 84. That means, again, in the base case, I've got too much air coming into the room. That's when they're on all full tilt. All the units are running full. Too much air. Therefore, my ratio is below 100. Now, I know I've got too much air. The problem, as I mentioned, it's going to cool off the return air to the heat exchangers, and that means my chiller is going to be less efficient. And the other 2 metrics that are popular if you take training like DCIM training, DCEP training, you will learn about these other 2 metrics, RCI high and low. RCI high is, do I have any hot spots? It's at 100%. I don't have any hot spots. So there's no hot spots in this data center. I'm certainly cooling it well enough. But if you look at the RCI low, that's looking at the low temperature metric. It's at 21%. It's too cold. I find a lot of data centers like this. Too much air being delivered at too low a temperature. And this is making the chiller go crazy, or the DX unit, or whatever it is, right? Because it's unhappy. It's not getting hot air back. It's still trying to deliver cold air, and it's working itself to death. That's a very common situation. Too much supply air, and supply air temperature is too low. This is what the room looks like. These are rack inlets. They are colored in accordance to conformance to the ASHRAE spec. The ASHRAE spec for a recommended temperature inlet, which maxes at 80.6. And 64.4 is the minimum. So these should be all green, right? But they're blue because they're too cold. They're failing on low temperature. Now, that doesn't kill your IT equipment because running them cold doesn't really hurt it, but it hurts your chiller and it hurts your heat rejection system. It means the energy consumption for that data center is huge because it's trying to deliver really, really cold air. The contours that you see here are not uncommon. We're delivering air through the middle, through the perforated tile. This is a raised floor data center. And you see the cold air coming up out of the floor, and as it gets to the top and it gets to the corners, it dissipates, and you don't have quite as much cold air there. So you do see a contour of temperature. That's a temperature plot. I wanted to also show you airflow coming back to the cooling units. Now, these are what we call path lines of supply. They're coming out of the floor. So the thing about this kind of modeling, this is CFD modeling, computational fluid dynamics. It's used extensively in aerospace and the automotive industries, and we're using it here. And the good thing about it is it allows you to visualize the air. It allows you to physically see it. And what we're doing here is we can see the air coming up out of those tiles and going up, and it should stop right at the inlet of those servers. It shouldn't go any further. If the air balance was perfect, if all I was delivering is what the system needed, there would be none of these returns going back. But you see they are. There's a few going back. I'm over-delivering air. I'm getting bypass airflow, and it's going back and it's cooling off my heat exchanger. And that's reducing my efficiency. So a perfect picture would be none of these returns going back, none of these yellow ones. And by the way, in yellow, I'm showing here a return temp of around 79 degrees, 80 degrees. Way too low. Remember, it should be, if my supply is 60, my return should be 80. If my supply is 70, my return should be around 90. There should be a 20-degree delta across the rack, if not more. It should be around 25, to be honest. The hotter the return, the better a heat exchanger performs. So we have too much supply air, and our supply temperature is too low. So first step we do, implement VFDs. To your point, let's get control of the supply air so we can modulate it based on the amount the IT needs. This is a good thing because in the early days of your data center, you don't have a lot of load, but maybe over time load goes up. You'd like to have a way to scale up and down the cooling capability and efficiency, and so VFD is a good way to do that. We're going to put temperature sensors in place on the racks to modulate the VFD. I like temperature sensors on racks. A lot of people do put pressure sensors under the floor to drive the VFD. And then they try to dial the floor pressure to be a certain level. This is a very common technique by people who put in air handlers. Use pressure to modulate the fan. The problem is the pressure is a proxy for temperature. It's a substitute. Really what we're interested in is temperature. We're interested in temperature of the rack inlets. So what you really want to do is use temperature, which I have done in this case. So I went ahead and did a run. This is a 1 megawatt data center, and the PUE dropped from 156 to 1.5. The RTI went to 90.28 from 84. It got better. The RCI high stayed at 100, which means I still have no hot spots, but my RCI low is still 21. I'm too cold now, but at least I got the airflow a little better balanced. And by the way, the predicted cost dropped by 50 grand a year, just put the VFDs in place and scaling them down a little bit. Okay? So things got better just from putting the VFDs in place, to your point. So, but we don't have air management problems yet here, but we don't really know because we haven't turned up supply air temp yet. As you start to turn up supply air temp, you're going to see things start to get a little bit. So here's what they look like now. So we were able to save 50K a year from putting the VFDs in place. We got better efficiency just from fans alone. Now the next step you always try to take is, can we begin to raise supply air temp? Using a modeling tool allows you to do that because you can try these what-if scenarios and experiment without the downside effect of burning up anybody's equipment. Doing it in the physical world, trial and error in the physical world can be a little more risky. Now here you see in this plot, this is the returns again, and you see there's fewer of these. There's still a few, but I'm not perfect in my delivery. So I got a few path lines going back, but certainly bypass airflow has been reduced and things are in much better shape. Next step, can we increase supply air temperature? And if so, what happens? So here we're going to increase supply air temperature by 8 degrees. So, and generally the way you do this in the real world is you step it up just a little bit at a time, maybe a degree every couple days, start to walk your way up and test and see and measure or wait for alarms to occur. But what happens here in the model is that as you begin to increase the supply air temp, because we're modulating it off temperature, in this case we use 3 temperature sensors on each rack, one at high, medium, and low across all the racks. Another substitute, if that's too expensive, is to put them across the top, because in this kind of design, that's usually where the issues are. But here we were able to increase supply air temp by 8 degrees, and the RTI began to go down a little bit because the fan started ramping up a little bit. So the total operating cost here remained about the same as the earlier run because the supply air temp went up, but the fans also ramped up and sort of counteracted that. But here's where we are. Racks are now all in conformance. They're within the specification. They're all green. A little bit of red right in those corners. That's a little bit hot, but you need not worry about it because generally you don't put servers up there in the corners like that. So that's generally okay. So what we were able to do here is roughly save $50,000 a year on a 1 megawatt data center by putting VFDs in place and getting the airflow balanced and also increasing the supply air temp just a little. And there's our final plot. You see there is some bypass airflow, about 18%. It's about as good as you're going to get without going to containment. If you were to contain it on the hot side, you could eliminate that bypass airflow and do a little bit better, or contain it on the cold side. Either one would work. In this case, I didn't do full containment. I just wanted to show you because not everybody has full containment, and furthermore, as I said, that does introduce some variables there too. So what we did, just in summary, is we took 3 steps. We first just added the VFD, so here's the base set of values right here. Our original cost to operate was about $1.4 million a year of operating cost. We put VFDs in place, it dropped to 1.40. We saved 50K, and then we brought up supply air by 8 degrees, and it remained about constant because the heat rejection system got more efficient, but the fans came up a little bit. Okay, so now it's a balanced system. Question?
On a thermal side, which is a better containment? Hot air,
So the question is, what's better, hot aisle or cold aisle? And the answer always is, it depends, right? It depends. I prefer hot because you want to get hot back to that heat exchanger. That heat exchanger wants a very, very hot return. And if you do give it a hot return, the chiller is going to be better, the maintenance is going to be lower, you're going to have better MTBF. Yeah?
So, in addition to that, I prefer hot aisle containment, because if you do cold aisle containment and your cooling quits, you're done right
You're
away.
cooked.
But if, literally.
You're cooked.
But if you have hot aisle containment, then all your common area
That's right.
becomes kind of a storage
It does.
location for cold air.
He's absolutely right.
Gives you a little bit more runtime.
He's got more volume. What he's talking about is volume. The ability to share, the ability to share somebody else's air. The cold aisle containment is a restricted volumetric area.
with respect to availability and downtime. I was speaking with respect to
Physics?
movement of energy consumption.
Energy consumption, it doesn't matter. From an energy consumption point of view, it doesn't matter. From a practicality point of view, hot aisle is preferred. However, hot aisle is a little tougher to implement in existing data centers because of cable trays and overhead stuff, and you got fire marshals in there, and it's a little more difficult to do hot aisle containment from a practical point of view. People love doing cold aisle. But the cold aisle issue is one Jeff talks about is problematic. If you lose anything, you're literally cooked. You got to start opening doors and stuff. I mean, you have to let bypass airflow go if you're not going to, right? The other problem in cold aisle I've seen as well is that you get temperature variations in it. Because it's a small area, if you have servers that are stacked a certain way, it'll blow by the first one, and the second one will grab it, and the first one starves, and you get hot spots in a cold contained data center because the servers are not uniform with respect to the fans. They're all running a little bit different. So I have seen a number of issues with that, all right? Now, the other thing here is our COP went up. I just want to point this out. Coefficient of performance improved. That means my heat rejection system got better because I moved my supply air temp up. So your efficiency of the whole system got better as a result of managing the airflow, slowing down the air and making it more closer to what the rack needs gives you 2 benefits. One, it reduces the energy by a ratio that's cubic in nature, all right, so that's big. And second of all, the heat going back to those return units is now higher, and that means they're more efficient, and that makes your chiller more efficient, your heat rejection, whether it's a chiller or a DX, or whether it's an evaporator, or whether it's an economizer. If it's an economizer, the window opens, right? Because now my heat rejection temperature is higher, so I have more days of the year the economizer will run. So in these examples, I'm assuming only mechanical, no economizer at all. If that unit, which is popular now, when you buy a new Liebert unit, they generally have built-in economization kinds of schemes, which means that window opens. So I have more days of the year that I can use it if I return hotter air to the unit.
Do you have a model that didn't have the end-row containment?
No, I don't have one here. I mean, it's easy to model. You can take them off. Yeah. The great thing about a modeler is it's quick and easy to do. All right, so now what happens at 50% load? And the reason I'm pointing this out is because prior to this point, not many people did 50% loads, right? When I work with design build companies, they all want to run it at 100%. Hey, let's build it for a megawatt. Let's build it for 10 megawatts. And guess what happens on day one? It's got much less than that in there, and the chillers are all screaming. So this is a 50% load, and we're going to design it for N+1. So this will run, and the question I'll simply ask right now, is it better to run 6 air handlers on this or 10? 6? 6? VFDs, remember, fan loss cubic, 6 or 10? So something to think about. Well, it does depend. It does depend, but in this case, it was better to do it with 10. So here, again, I'll just run through these. I know you can't read them because they're small. So this is a 1.62 PUE, and the RTI is 67. So when I see an RTI of 67, I already go, uh-oh, we got way too much air. So we need to back the air down. I know that the RCI high is going to be fine because we've got more air and it's too cold. But look at the RCI low, 21%. It's just terrible. Estimated cost to operate about $760K per year at 50% load. We've got too much air, supply temp too low. This is generally every time I enter a data center I see that. Supply air is too high, the supplier volume is too high, and the supply air temp is too low. Yeah? I did not in this case, and I probably should have, but I did not in this case. Yep, yep. So, you know what? I guess I did, because I took them out. They're not there. So yes, I did. I couldn't remember. But here, same case, way too much return air going back there. This is just a visual representation of it that's showing.
With just the end caps, Paul?
That is with the end caps. Yeah, they're in place. They're transparent, but they're there. Yep, yep. Again, to know how much you need, how much air you need, rule of thumb, 125 CFM per kW. Fairly easy math to do. I put temperature sensors at 3 points on all the racks, and I set the control system so that it triggered off max temp. All right, so wherever it measures max temperature, that's the sensor it's going to use to drive the VFD to the proper level. And immediately things get better. So what happens here is my RTI is now 97, got much better, closer to 100. Remember that requirement, rack inlet is in the numerator, rack requirement is in the numerator, so you want a higher number. 97 now, that's pretty good. RCI high is 100, that's pretty good. RCI low, 22, 23. Yeah, too cold. So now I've got the airflow right, but what do I do about temperature? Can I drive temperature up? So using the VFDs in this case saved $100K a year in operating cost. By the way, assuming a cost of electricity of 10 cents in this particular case. But, yeah. So then you start to modulate. Now in this case, I'm using just 6 units. You see them right there, 3 on a side, and modulating those fans and driving that system. Getting a little bit of bypass airflow there, not a whole lot. And things got better. So we dropped down to 653 against 669. So running all of the air handlers, that's the question we had, running all the air handlers with 10 AHUs, air handler units, actually lowered the cost of operating this data center as compared to 6. And that's just because of the fan law. All right? So running 10 units at low speed costs less than running 6 units at a higher speed. Just like shutting units off is not as efficient as running them at low speeds. So because the first thing you think of is, let's turn these units off, we're not using them. But because of the fan law, it actually turns out numerically that it's less energy to run them low than it is to shut them off. So better to run 10 at low speed than run 6 at a higher speed in this particular case.
Paul,
Yeah?
Does it make any difference if you partition off, in your example, partition off the subfloor where there is no racks, not taking into account leakage through the floor?
No, it doesn't do any good. Doesn't make a difference.
That's what I thought.
Yeah. So the question he had is, does it, subfloor partitioning. I'm not an advocate of subfloor partitioning, and it wouldn't work in this case. It wouldn't help, assuming, as he said, not a lot of leakage through those tiles. Tiles don't leak too bad, by the way. The leakage on sealed tiles, raised floor tiles, is fairly low if they're put in correctly. They're engineered to be tight, and as long as they're good against the walls, that's usually where the issues are, is up against the walls. They generally hold up pretty well. Leakage in the range of a few percent, not too bad. So leaving it all open in this case worked better. If you start putting subfloor partitions in to try to manage airflow, the biggest problem is you forget they're there. Somebody forgets they're there and then starts to try to do something and it doesn't work and they can't understand why and it causes all kinds of issues. So engineered solutions that are good for one case but not good for general cases tend to make me a little uneasy. Okay. So here's the result of the 50% load. We went with 6 AHUs first. That's full speed. Everything running. The cost to run it per year was predicted to be $760K, almost $750,000. And then we put in the VFDs, still running it at the same supply air temp. We saved some. It dropped from 760 down to 669, so we saved quite a bit of money there. And then we went to 10 AHUs, and we saved a little bit more. We went from 669 to 632. I have to get close to see it. And then we rose supply air temp just a little. Now, when you go up on supply air temp, the fans start to come up a little bit because they're sensing max temperature. And so that ended up being a wash with respect to cost. We went from, well, a little bit, 632 down to 611. And that's because the efficiency went up. Now, again, the efficiency went up of the heat rejection system because it was getting higher return air temps again. Now, I don't have an economizer in this thing at all. If I did have an economizer in this model, then all of a sudden it would be a great savings because, again, that window of opportunity opens with respect to the number of days per year I get to use that economizer. So I would advocate probably for that latter case for that reason. Yes, that's true. It does depend where you are. Economizers do vary depending on location. But they are being included now in a lot of components, you know, Liebert components and Stoltz and so forth. So in this case, we're able to save 20%, $148K a year. Saving 20% on data center operation is a fairly easy thing to do. I mean, I know people who are in business like mine on the practitioner side or the implementation side, and they'll tell you they can go in and save you 20 to 25% through air management pretty easily. In fact, the LBL articles that were written quite some time ago talked about 20 to 30%. Airflow management is the low-hanging fruit. It's the easiest place to save money. Much easier than buying another air handler or, you know, much less cost and can work very well. So, airflow management. And that's about it. I'll open it up for questions, just some summary slides here. Using CFD is really just a tool. It's a decision support tool. It allows you to understand the implications of change. What happens if I raise the temperature? What happens if I put containment in place? What happens if so it's a what-if tool or a decision support tool. It's not a panacea, it's just a tool. It helps. It's not perfect. It's not a forensic tool. Some people like to use it for that. So 3 things you learned: how to predict energy savings based on an optimized airflow, how cooling efficiency affects overall PUE. It's kind of the elephant in the room. And what parameters do I look for and can I think about? One of them is, as I mentioned to you, what's the efficiency of your current system? Fairly easy to figure out. You know your IT load. Go look at how much the cooling system is pulling. And generally it's on a transfer switch because you want to keep that cooling system going in the case of down power. So it's sitting there and it's on a transfer switch. You can go measure it. Ratio those 2 measurements. If they're not close to 4, if they're 3, if they're 2, if they're 1 to 1, you've got a lot of opportunity for savings that you can make with fairly modest investments. And here I didn't do any hard containment. I did it on purpose. I wanted to show you that it can be done without hard containment. All they did, and in fact, this one I learned about the first time I saw this, what they had done is gone to Home Depot and bought plexiglass with magnets on it and stuck it on the ends of those rack rows to keep from recirculating. It doesn't have to be elegant. And it worked. They were seeing a PUE of 135 in that room using exactly that design. Just letting the air float up, go into the ceiling, returns, and modulating the supply air as best they could. So it can be done. I've seen it done. So that's contact information for me. We do have a booth here, 238, if you want to stop by and talk about it. I'll be around. I'm here to take questions. If there are any questions, I'm certainly willing to. It was quite a bit of material that we covered in a fairly short amount of time. So any questions?
Thank you, Paul.
Sure.